promised Omar that I would not make jokes about his name, but then I went online to, I stalked him online to actually make sure I had all his characters right. And the first thing I found is Google told me not to be confused with Hurricane Omar. Anyway, so actually he just told me this is the second talk on the NIF result. The first having been to the International Atomic Energy Agency, virtual in Vienna. So actually that's a real honor to have be the second one to actually get the talk. Omar is a chief scientist for inertial confined fusion at Livermore Lab. He has a bachelor in physics and applied math from the Metropolitan State University in Denver, and then a PhD in physics from UCLA. He was then postdoc at UCLA and joined Livermore in '98. He was also, for about a year, a SciSac fellow here at Stanford. That was in 2010 or 2011 or something or thereabout. He received the Ernest Lawrence Award of BOE, probably from Steve. Where is Steve? Yeah, so you were. And he's a fellow of the ABS, and also most recently received the Teller Award of the American Nuclear Society. And with this, thanks, welcome to Stanford. Thanks for.
Okay, thank you for inviting me. And everybody can hear me in the back of the room? All right, super. All right, so let's start with some conclusions and the takeaway from this talk. The recent NIF experiments involving inertial confinement fusion I regard as an existence proof of laboratory ignition and target gain. So let's go through the conclusions. We're finding that there are no mystery physics obstacles standing in the way of ignition or gain, and I'll explain what those terms are later in the talk. The theoretical predictions of where the key physics parameter regime where ignition was expected to occur are actually consistent with our results. We found that additional laser energy at fixed laser power, which is opposite to conventional thinking, was very beneficial. Implosion physics, and I'll talk about what implosion physics is in this talk, turns out to be a lot more sensitive to engineer control of the laser and targets than we originally thought. So far, we've had trouble with very high gain, high compression targets, and they just haven't worked as we expected them to, and that forced us into a different strategy to get ignition and gain to work. So all the breakthroughs that I'll be talking about over the last decade that are squeezed into this talk are using what we call low gain designs. But the remarkable takeaway, if any of you follow that joke about fusion always being 20 years away, it's now remarkable that burning plasmas, ignition, and scientific break-even can all be discussed in the past tense as of last month. So, what are we trying to do? We're trying to assemble a configuration of fusion fuel that looks something like this. It's a scale of about 100 microns. We're trying to make a hot plasma surrounded by a cold DT shell. And we call the hot plasma the hot spot and the cold shell the fuel. We're trying to capitalize on the DT fusion reaction rate. So deuterium and tritium, which are isotopes of hydrogen, they're known to fuse into two particles, producing a neutron, which carries away 80% of the energy, and an alpha particle that carries away 20% of the energy. If we can create conditions inside this hot spot that are capable of stopping these alpha particles, what happens is the following. This is a plot of fusion reaction rate versus temperature. There's several different fusion reactions plotted here. We're interested in the blue one here, which is the DT fusion reaction rate. So if we stop those alphas produced in DT fusion inside the plasma, they deposit energy inside that plasma, which creates heat, and that can cause the temperature to go up. Well, if the temperature goes up, because of the nature of the fusion reaction rate, we get more fusion reactions. Then if we are able to stop those alpha particles in the hot spot, we get more heat, and we can get the temperature to go up yet again. And because of the nature of the fusion reaction rate, we get even more reactions out. This process is called self-heating, and if it is intense enough and rapid enough, we get a thermal feedback loop, and that's what we call ignition, and that's how ignition is generated. The conditions to get these alpha particles to stop in our fusion plasma are pretty intense. They're not something you normally find lying around anywhere. We need a hotspot areal density, that's the density times the radius of over 0.3 grams per centimeter squared, a peak central density of over 100 grams per centimeter cubed. Keep in mind the density of gold is about 19 grams per centimeter cubed, so it's many times the density of gold in the center. And the pressures are of order 400 or more gigabars, which is over twice the pressure at the center of the sun. So that's what we're trying to do. How do we do it? So we use a process that we call indirect drive inertial confinement fusion, and that's what ICF stands for. We're going to go through these cartoons here. We actually are trying to use X-rays to ablate and accelerate a capsule of fuel to extreme velocity and create that configuration I was just describing on the previous slide. So here's an example of what one of our targets looks like. These are the laser beams entering from the top and bottom of our target, and that's the source of energy for our target. This can, this is a metallic can made out of materials that are high up on the periodic table. Gold and depleted uranium are some of the materials we use. And here's what we call the capsule inside that can that we call the Hallraum. Inside the capsule is our fusion fuel that eventually we're going to crunch up into the state I described on the previous slide. Okay, so what happens here is the lasers deposit energy into the Hallraum through apertures at the top and bottom. We call those apertures laser entrance holes. Those lasers touch the inside of the wall and deposit energy and are converted into a bath of X-rays. That bath of X-rays then causes the exterior of the capsule to explode. That's what we call ablation. It's basically ionizing the material. The electrons and ions separate. It creates high pressures of order of 150 megabars. That's 150 million atmospheres. That causes the capsule to squeeze inwards upon itself and accelerate to very high velocities. We call that phase of the target operation the implosion. Eventually, that capsule runs out of anywhere to go because it's just squeezing in from all sides. And the kinetic energy that it gains upon being accelerated has to be then transitioned into internal energy. We call that phase stagnation. So getting the conditions we need for a rapid increase in fusion reactions requires a lot of precise control of the design of this system in terms of what we're asking from the laser and from the target. And careful control of all those parameters. Okay, so let's talk about what some of these terms are, because these terms are often conflated and it's actually very confusing, especially if you follow the press. So burning plasma, ignition, and gain actually all mean something physically different. And so it's actually improper to use them interchangeably. So let's go through what these terms are. Burning plasma in the context of inertial confinement fusion is when the self-heating that I described a couple slides back, the energy from that self-heating process actually exceeds the external PDV work that we use to compress that capsule down to small scale and get the temperature and density up. This is very analogous to the concept of a burning plasma in magnetic fusion energy, where the self-heating energy exceeds the external heating to the DT. The difference between inertial confinement fusion and magnetic fusion is magnetic fusion, fusioneers have many ways of heating their plasma. In ICF, we just have that implosion, which is doing mechanical work to squeeze up our fusion fuel. Ignition, by ignition, we refer to something called the Lawson criterion, which is a paper back in the 1950s. This is a condition where the self-heating power in the DT plasma exceeds all the power losses in that plasma. Well, what are the losses in this plasma? If you take anything and try to heat it up, it tends to want to radiate that energy away. In our case, the radiation comes out in the form of X-rays. There's heat conduction. Heat wants to go from where it's hot to where it's cold. So electron heat conduction in particular is the process that tries to cool off our hot plasma. And negative PDV work. We squeeze up this gas to get it hot and dense, but then eventually it blows itself apart, and that negative PDV work is also a loss. And so we are trying to compete against all these losses, and that if we are able to do that, ignition occurs. Well, what is ignition then? It's this thermodynamic instability that we observe in the temperature and the yield, where we see an explosive increase in those quantities as the self-heating outstrips all the losses. Target gain is different, actually. Target gain means that the fusion yield that we've got out of our fusion system actually exceeds the laser energy into the target. But it actually turns out that the 1997 National Academy of Sciences actually defined target gain as ignition and in a report, and the US Department of Energy actually adopted that definition of ignition. But in our physically, they're different processes, and in our publications, they're different. Actually, you're responsible. I really want to talk to you about that, by the way. It's you and, yeah, we should talk about that. But so if you listen to our talks and our publications, we make this distinction, but be aware in a lot of government documents, these two things are mixed together. All right, so I went through the cartoon of how an ICF target more or less works, and we'll see more about that later. Let's now talk about the laser, which we use to drive these targets. The laser that we have at Livermore is the National Ignition Facility, and it's a facility about the size of 3 football fields. So if you go from this end to this end and put 3 football fields side by side, that's the system. It's broken into several components. Let's just go through them quickly. There's a set of capacitor banks on each side of the system that are charged with electrical energy. In particular, there are 300 to 400 megajoules of electrical energy in these capacitor banks. At this end of the system, you have preamplifiers for the laser that then feed laser light into the main amplifiers on either side of the facility. The laser light bounces back and forth through flash lamps, picking up energy before entering this part of the NIF system, which we call the switch yard. The switch yard is composed of tubes with mirrors in them that reflect the light into a target chamber within which our target resides. Just before entering the target chamber, the laser system is actually mostly red light, and it's about 3 megajoules of red light that enters a component called the tripler. And the tripler converts that red light into blue light just before entering the chamber. We call that light 3 omega light. It's 351 nanometers of blue light that's actually shot at our target. That blue light that enters our target is only 2 megajoules, so we've already lost a megajoule by going through that tripler. And there's an example of our target. It's a picture with some human fingers in the picture to give you an idea of the scale. The target is about 1 centimeter in length, and again, the laser enters through the top and bottom of that can, which we call the Hall-ROM, to deposit energy inside the can to make X-rays. We only get about 250 kilojoules of X-rays from that 2 megajoules of laser light that was shot in, and those X-rays are absorbed by the surface of the capsule. Again, the picture is shown with a human hand or a human finger to give you an idea of the scale. That capsule is about 2 millimeters in diameter. Inside the capsule is our fusion fuel, and only 20 kilojoules of energy actually make it into that fusion fuel. So we've gone from 300 to 400 megajoules of energy to 20 kilojoules of energy before the fusion fuel sees it. So there's a dramatic loss of energy going from here to here. So, but why do we do that? Well, the whole principle behind inertial confinement fusion is energy compression. So we knowingly sacrifice energy for energy density, and that's the nature of ICF. Because there's that huge cascade of energy loss going from the capacitor banks to the fusion fuel, it actually means that there's more than one way to define gain. Again, gain is just energy out compared to energy in. So in practice, for those of us who work in ICF, there are 3 gains that we talk about, and they're illustrated in this figure on the right. Again, here's this target. It's the Hall-ROM, which is the metal can that that converts the laser light into X-rays. You can define a gain for that target, which is the fusion yield over the energy delivered to that Hall-ROM by the laser. Inside is the capsule. So you define a capsule gain to be the fusion yield over the energy absorbed into that volume, and inside that capsule is the fusion fuel, shown in blue. You can define a fuel gain, which is the fusion yield over the energy delivered to the fuel. And the reason why these different gains are important is because, again, there's this big cascade of energy from outside in, and all these volumes are considerably different. Nevertheless, all of these capsule gains have increased by a factor of about 5,000 over the last 10 years. What I'm plotting here is fusion yield over the kinetic energy into the fuel, so that's most analogous to fuel gain here. And I'm plotting it, the x-axis is a little funny, but it's pressure times confinement time times the plasma temperature to the 1.6 power with a factor that has to do with the balance of energy between the fuel and the hot spot inside. It's a factor of order of 0.6 or so. So you can see that over this 10 years, we've gone from these points down here to this point up here. We actually passed fuel gain greater than 1, which again is this innermost metric back in 2014. We passed a capsule gain greater than 1 in mid-2021, about a year and a half ago. And most recently, last month, we got target gain greater than 1 in December 5th, 2022. So our best results as of yet are a target gain of 1.5, a capsule gain of 12, and a fuel gain of 160. Okay, so the big takeaway here is that just because we get gain greater than 1, that does not mean we've made net energy, because there's a lot of energy consumed by the facility, which was the point of the previous slides. It's a huge accomplishment nevertheless. So how did we make that progress of a factor of 1,000 over 10 years? And I'm going to tell you about some of the key challenges we faced and how we addressed them. The key challenges we faced with regards to the target physics are instability control, symmetry control of our implosion, and these will make sense further on into the talk, sufficient energy coupling to our target quality, and ultra-high compression. So those are the main physics or applied physics challenges which have frustrated us. So some of these processes or frustrations, we had some idea of how to control through what we call the laser pulse shape. And so let's talk about the laser pulse shape and how we implement control over our implosions. A typical laser pulse shape is shown in blue here on the left. This is laser power in terawatts, starting at a small value, a low level that we call the picket, rising to peak power, and then turning off at late time. Because we're shooting the laser into that metal can, that Hall-ROM, our capsule doesn't see that laser energy directly. It sees the X-rays that are made by the laser hitting the Hall-ROM and heating it up. So the laser pulse becomes a radiation temperature source, which is shown in red. And you can see there are a bunch of wiggles in it, and these wiggles all do something different to our target. I'm going to talk about the three main parts of this laser pulse and what they do, and also to introduce you to some of our jargon, because we do have quite a lot of jargon, and I'll probably slip into some of it during the talk. The first part of the laser pulse, the early time part, we call the foot. What the foot does is it actually controls the stability of the implosion and the majority of the fuel entropy. Entropy, we measure that through a quantity called the adiabat, and you'll see in some of the equations that's denoted as alpha IF. IF stands for in-flight, which means the adiabat at peak velocity. Adiabat is a measure of squishiness. So a high adiabat gas is one that it's hard to compress. A low adiabat gas is one that's easy to compress. Because the laser energy that we're shooting into the Hall-ROM makes a radiation temperature, and the radiation temperature is related to the pressure that's causing the outside of the ablator to explode, we can launch shocks into that system. So generally, a high foot, this region will launch a strong shock that will cause a big entropy change and give us a high adiabat. If we have a low foot, the radiation temperature in the early part of the pulse will be lower. The response of the ablator to that will be a lower pressure, and you'll get weaker shocks, and you'll have a lower adiabat. The peak power part of the laser pulse, which is corresponds to this mid-level of radiation temperature is actually what accelerates the implosion inwards. Again, you're doing work on the implosion, so the pressure is a force, provides a force. And so the peak power is mostly responsible for implosion velocity. And then finally, as the laser pulse turns off and the hull realm starts to cool, we have this period of time here that we call the coast period or the coast time. And it actually ends up being a lot more important than people thought. And it's responsible for the efficiency of converting the kinetic energy the implosion acquired in flight into internal energy. And the key quantity that it controls is the radius at which the implosion acquires its peak velocity. Other parts of the ablation pressure have to do with the material that we make the capsule out of. The average atomic number and atomic mass play into the ablation pressure, and the tendency of the material to reject X-rays through a quantity called the albedo also influences the ablation pressure. All right, so going in, we thought we knew what we were doing, and we can control everything about the implosion that we needed to control, and that resulted in something called the low-foot implosion, which were part of the National Ignition Campaign, which was a campaign of experiments in 2010 to 2012 where we thought we would be able to get high fusion yields out of this whole integrated system, but it underperformed. It just didn't work. So I'm going to show you a series of plots to kind of tell the story. This is neutron yield in terms of neutron number versus ion temperature on the x-axis, and the right plots are going to be total fusion yield versus hotspot pressure. The only difference between this fusion yield and this fusion yield, this is in terms of neutron number, this is in terms of kilojoules. But they're equivalent. There's a direct equivalence, so whichever one means more to you is the one you should look at. What you can see here is instead of getting megajoules or tens of megajoules of fusion yield, we were getting kilojoules of fusion yield. There was no apparent pattern in the data, very little pattern at least, and it just wasn't working. And it turns out that these experiments performed for a number of reasons, which we had to tackle over the subsequent 10 years. One of the primary processes that were defeating the success of those implosions is a hydrodynamic instability. We sometimes also call this Rayleigh-Taylor instability. This is the tendency of materials of different density under acceleration to want to change places with each other. Or, for example, buoyancy is a form of Rayleigh-Taylor instability where hot air rises and cold air falls. The hot air and the cold air want to change places. So we understand the physics of Rayleigh-Taylor instability pretty well. It's pretty ubiquitous. In our case, we tend to call this process ablative Rayleigh-Taylor instability because the ablator, which is the outside surface of the capsule, tends to be particularly sensitive to it. The growth rate for ablation Rayleigh-Taylor instability goes something like this. Goes as the square root of the wave number times the acceleration. That's the classical Rayleigh-Taylor growth rate. And it can be mitigated by controlling the density gradient scale length and the ablation velocity. There are numerous forms for this equation. What this equation basically says, though, if you have a small perturbation and you have a positive growth rate, the small perturbation becomes a large perturbation exponentially in time. And that's a problem. The best way to see how this works is to see this movie here that will summarize it. So what you're seeing here is a movie of ion temperature on the left, density on the right. We're picking up our implosion at peak velocity. You can see there are a lot of small little bumps on the surface, and you're going to watch those grow aggressively and basically destroy this implosion. So what happens here is, again, we want to have a hot center region surrounded by a cold fuel. That's what we want. But because of this tendency of Rayleigh-Taylor instability, the implosion basically turns itself inside out. So the hot central region where most of our fusion was supposed to occur is gone. The shell of colder material around it is shredded. That's basically Rayleigh-Taylor instability, and that's why it's so catastrophic. The problem is we need to get high velocities if we want to get high compression, and we want to get high temperatures, and that means we need high acceleration. So we have no choice but to deal with Rayleigh-Taylor instability. So the way we deal with it is to try to increase the density gradient scale length and increase the ablation velocity, and that's a way to fight back against Rayleigh-Taylor instability. No, we never get rid of it completely. But this led to something we call the high foot implosion, which was the next step in this story. So in the 2013 to 2015 period, we implemented this idea of a high foot implosion, which does exactly what the name says. That early part of the laser pulse that we call the foot, we make it higher. That higher foot means there's a higher radiation temperature early in time, and that tends to smooth out some of the initial wrinkles that want to form under the action of Rayleigh-Taylor instability and give us a better chance of surviving. So again, if you look at fusion yield versus ion temperature, these high foot implosions actually increase the performance of, by a factor of 10, and we were able to finally get high pressures at the center of the implosion that were rivaling the pressure at the center of the sun. So this was a rather enormous step forward in that period, but it was still far from ignition. We're still nowhere close to the megajoule levels of yield, but it's like the 10 to 20 kilojoule level, still far better than the 1-ish that we had before. This tactic did not solve all of our problems, though. What we saw in our implosions that we were able to control Rayleigh-Taylor instability in is that we had asymmetry problems. So we did some experiments with these high foot implosions and a couple of series of experiments. One set of experiments that was repeatability experiments, excuse me, where we want to determine, can we learn anything from these implosions beyond the fact that Rayleigh-Taylor instability really was,
Are these pinhole pictures?
Yeah, I'll explain. These are pinhole pictures. This row of pictures is our X-ray emission through pinhole that are the high energy X-rays, kind of in the 20 keV range that you pick up on CCDs. And so this is time integrated. So you're seeing a time integrated picture of the emission of the hot spot of the implosion. These are basically neutron pinhole images. So you're actually imaging neutrons here. The red are 14 MeV neutrons. The blue are downscattered neutrons. So this is giving you an idea of the morphology of the hot spot and the cold fuel around the hot spot. It's not quite that simple, but it's giving you some idea of that. This is fusion yield that we measure in kilojoules, and this is temperature. We did a couple series of experiments at low power, low energy, and then higher power, high energy with these high foot experiments. The bottom line here is these experiments with the high foot were reasonably reproducible. It's a bit of a qualitative metric. The yields are all about the same, temperatures are all about the same, the shape is mostly the same, except for one shot here where the laser misfired. But nevertheless, these high foot implosions, by controlling Rayleigh-Taylor instability, were repeatable enough that we might be able to learn something else from them, and so we did. So what we did is a series of experiments that then revealed the importance of the coast time, that late part of the laser pulse. So this is an example. This is laser power versus time. We have 3 pulses here. The blue is the baseline shot, and then we have a higher power version of that and a lower power but extended duration of peak power version of that. We wanted to see which of these tactics was better. The conventional tactic for ICF is you need higher power. That's what most people generally think. It actually turns out to be the opposite of that. By reducing the power and extending the duration of peak power, which is the red pulse, we're actually able to increase the radiation temperature at late time compared to the other 2 cases. And we saw a significant increase in stagnation pressure at the center of our implosions by doing that. So this is a plot of stagnation pressure versus coast time. After we did this initial test, we decided, well, let's explore this further, and we did a whole series of experiments where we steadily reduced the coast time. And again, the coast time is the duration between max compression of the implosion, where it's producing its maximum yield, and the end of the laser pulse. By reducing that, we got a dramatic increase in stagnation pressure. which is important for getting to the conditions needed for ignition. We understood why this was later. Our understanding was basically an empirical observation initially, and we understood the physics of this much later. The particularly relevant bit of physics that this tended to influence is the radius at which the implosion acquired its peak velocity. So if you ever, I hope everybody knows how to drive in the audience. So what are you taught when you're driving on the freeway and you see an accident up ahead? You know, you're supposed to look way ahead, and if you see something going on, you kind of gently put on the brakes and slow down the car gradually, okay? That would be a long coast time. Okay, but what if you're a crazy driver and you just scream right up to the accident and slam on the brakes? Okay, what happens is you cook your brakes when you do that. An ICF implosion, you want to cook your brakes. You want to race in as fast as you can, as far as you can before slowing on the brakes, and that's a way to maximize the conversion of kinetic energy into internal energy, and that will give you a much higher pressure at the center of the implosion and much higher temperature. And that's kind of why this radius of peak velocity is so important. And in equation form, it shows up here. It goes as the pressure goes as 1 over the square of that radius of peak velocity. So we learned two important things with the high foot implosion. Minimizing coast time is important, and controlling, we need to control ablation Rayleigh-Taylor instability much better than we did before. But we still had this symmetry problem. So the next epoch of experiments that we undertook on the NIF were to switch from plastic ablators to what we call high-density carbon, which is a euphemism for diamond. I think there was really some public relations involved in that naming, because if you're blowing up gold and diamond, it just doesn't sound very cost-effective to the public. So it's high-density carbon. The physics reason for doing high-density carbon is it has about 3 times the density of plastic. So high-density carbon has a density about 3.5 grams per centimeter cubed. Plastic was 1.2 grams per centimeter cubed. So for the same mass of ablator, we could make the shell thicker, and thinner. And by making the shell thinner, we could make the laser pulse shape shorter. And the reason why we wanted to do that is we already suspected by making the laser pulse shape shorter, there's less time to create plasma inside the Hall ROM, and maybe we would have better success controlling symmetry that way. So we did that. We switched the Hall ROM. We switched the laser pulse to shorter laser pulses. We used diamond ablators. We also changed the gas fill in that Hall ROM because they kind of go together. And we did see an improvement. We saw about a factor of 2 improvement in yield and about a factor of 2 improvement in hot spot pressure. But then we couldn't go any further. The yields basically got stuck again. The pressures got stuck again. And while we were able to improve our ability to control symmetry, we didn't have perfect control of symmetry. And in fact, today, we still struggle with controlling symmetry in our implosions. And so this is a set of images to just kind of show you the zoology of the symmetry challenges that we've had to face that we still face today. So the top image are actually neutron images again, but it's a different type of neutron image called a fluence compensated downscatter image. So this really is a better way to see the shell of cold fusion fuel that surrounds the hot spot. You can see this one's kind of round, but the others have different morphologies. This is the same sort of image except from a computer simulation that's best matched to the experiment. And this is basically looking directly at the simulation, seeing what the density is and the temperature is. This was published by my young colleague, Annie Kreitcher. So we still struggle with implosion symmetry control even today. So why is this important? I keep saying symmetry is important, but I haven't shown you why symmetry is important. It actually all comes down to energy. As I tried to articulate at the beginning of the presentation, where we talk through the different phases of energy loss of the NIF, we hardly get any energy into our fusion fuel. It's the nature of an ICF system. It's just the way it works. So energy is precious. We can't afford to lose energy. That's illustrated in these 2 plots here, and I'll try to tell this story. It's really essential for ICF to maximize the conversion of kinetic energy into hotspot internal energy. We saw in our database, if we look at fusion yield versus energy in the hotspot, which is that hot core of our plasma, and we can infer this quantity from our data, that the fusion yield actually does increase as we get more energy into the hotspot. There's scatter here. This is log scale. So but in an ensemble sense, we see a very clear increase of fusion yield with hotspot energy. The scaling goes about to energy to the 3.3 power. But for decades, our computer simulations have shown, well, if you have any asymmetry, the yield is going to go down. If you have increased asymmetry, it can go down a lot. If you can decrease the asymmetry, you can kind of get back to a 1D implosion, which is the best case. You can put this together. What's interesting here, this scaling also has a 3.3 power. So that's because they're connected. We understood this later, that the hotspot energy is kind of a combination of the kinetic energy we put into the implosion and a measure of asymmetry that we call normalized residual kinetic energy, and that'll mean more in the next couple of slides. So we can put in as much kinetic energy as we want, but if we have asymmetry, we defeat ourselves. So we really have to minimize asymmetry while maximizing kinetic energy in order to have any chance of success. Okay, so by the way, this physics picture or this realization of energy in the hotspot being important led to what's called the hybrid strategy. And hybrid is an acronym. It's actually a double entendre because it literally meant let's kind of hybridize the best ideas that we've seen work in our experiments up to this point. But it also means high yield, big radius implosion design. Why big radius? Because we want to increase the mass of the shell. Why not increase the velocity? We were already pushing the velocity as far as we could go and control this instability. So the only levers we had left are control symmetry better, increase the mass of the shell. You can make the mass of the shell bigger by increasing the radius or the thickness or both. And that's put us kind of on this last part of the strategy that got us to where we are today. But before we show that, let's understand what symmetry does better. I find this particularly cute. This is basically freshman physics, and it takes a lot of the mystery out of why asymmetry matters. So forget about those funny morphology 3D implosions. Let's make a simple implosion system that you can write down some equations for. So let's just imagine two pistons that are our shell or our blader, and they're shooting towards each other with a velocity and squeezing up our fusion plasma in the middle. At some point, you know, those pistons basically squeeze that gas up till the gas refuses to be squeezed anymore, and that's the minimum volume of the gas. What happens, you can write down conservation of energy, you know, 1/2 mv squared for this piston, 1/2 mv squared for this piston. The energy of the gas inside is 3/2 pressure times volume. All the freshman physics people should know that. And then you write down conservation of momentum, you know, mass times velocity to the left plus mass times velocity to the right has to equal the mass of this combined object with whatever center of mass velocity it has. Conservation of momentum, conservation of energy. You can write down an equation that tells you how the pressure in the central gas at stagnation should increase. And it's related, again, to the kinetic energy, the mass of the pistons, the velocity squared. We want to minimize the volume. The adiabat has something to do with that. But then there's this term off to the other side that says if you have any center of mass velocity, you degrade the kinetic energy that you've tried to put into the implosion. And the larger the center of mass velocity is compared to the implosion velocity, the more significant this energy loss is. And you never get that back. Conservation of momentum says once you have the center of mass is always going to move at that same velocity, and you'll never get that back. So that's wasted kinetic energy, and that's why we call this residual kinetic energy. Now you're going to say, oh, that's a simple model. That's not really how it works. But if you compare this simple toy model to our simulations and our data, it actually works quite well. So it explains why symmetry, at least in this mode 1, which is just a translational motion, matters. You can now generalize that picture to higher dimensions and also understand how higher modes of asymmetry kill you. It's basically the same picture, but now 3 dimensions. And actually, the math becomes a little harder, but it's still fun. Trust me on that. And the key quantity that's a metric for a symmetry ends up being an inverse average of the rho r of each of these pistons. That's the areal density. We call this type of average the weighted harmonic mean. And this parameter, again, actually does seem to actually match our simulation database very well. You can see these are different. You don't have to be an expert. You can see this is getting more asymmetric. You use this weighted harmonic mean, and that matches our simulation. So now we can understand why asymmetry is so damaging. It's basically wasted energy, wasted kinetic energy. All right, so this is why we have to control it. Well, we always had some idea of how to control symmetry in these ICF implosions, these indirect drive implosions. So let's talk about this image here. Again, we have a cartoon now of our Hall-ROM with our capsule inside. We have laser beams shooting in. The primary way to control asymmetry in these indirect drive implosions was to point the laser beams at different positions on the wall. I'm only showing 2 of the laser beams. Of course, there are 192, 96 on the top and the bottom, but just to illustrate the physics. And you would point those at different locations. Those lasers would hit the wall, convert to X-rays in that location, and you can control the X-ray flux that the capsule sees. Imagine you standing on the top of the capsule and you see the sky of X-rays. So you can change the brightness of the sky and try to control the implosion. What we realized during this period from 2015 to 2018, it's not that simple. We understood what was going on finally. That the outer, what we call the outer, this is jargon again, the outer laser beams, which are these shallow angle laser beams coming from the NIF, were hitting the inside of the wall. You know, you're blasting this material with the laser beam, it explodes into a cloud of plasma. That cloud of plasma was then flying inwards and then interfering with what we call the steep angle beams, which our jargon is the inner beams. So we were actually scraping off some of the energy of the inner beams that we meant to go here and stopping that energy here. And that was frustrating our ability to control symmetry with only pointing. So there were 2 key realizations during this period from 2015 to 2018 that allowed us to master symmetry control better. Again, not perfectly though. One has to do with understanding the key physical properties, parameters that influence the basic mode 2, which symmetry. And when I say mode 2, think of a pancake, which is an oblate mode 2 symmetry, and think of a sausage, which is a prolate mode 2 symmetry. We found, and actually my colleague Debbie and Joe Ralph found, that if you could, all of our database from all our experiments would collapse on a line if we wrote things in terms of this parameter here that has to do with the square root of the amount of energy delivered to these outer beams, the area on the inside of the wall of those beams, the fill density of the Hall-ROM, which is basically a helium gas, the time duration of the laser pulse, the radius of the Hall-ROM, and the radius of the capsule. It's complicated. There's actually a fairly simple way to understand why this would be the parameter of interest based on the physics of this cloud ingressing inwards, but we don't have time in this talk. Nevertheless, all of our data falls on this curve. So now, with this understanding, we could actually jump pretty close to what an optimal design is, and then do some finessing with experiments to actually get the symmetry zero the way we want. The reason why this is important is the computer models don't always get this right. The computer models don't get this right, and they don't get the propagation of the laser beams right. So we had to do this part empirically. The other key realization from this period is that we could use cross-beam energy transfer in these low-gas fill Hall-ROMs to force energy from these outer beams to these inner beams. Cross-beam transfer is a laser plasma instability process where Mother Nature is trying to frustrate you and take energy and put it where you don't want it. This is a case where you actually can use Mother Nature's mischief against her and to your benefit. So by changing the wavelength by 1 angstrom between these 2 sets of beams, you could force energy from the outer beam to the inner beam. We weren't sure it was going to work with low-gas fill Hall-ROMs. The set of experiments done and published here shows that it does work quite well, and we were on our way. So we get a gross design for a Hall-ROM that will give us symmetry control with this, and then we tune it up with this, and away we go. So we thought we were all set to implement this hybrid strategy that allowed us to make the shell of the implosion bigger and get more energy in. And we did it. So in 2018 to 2020, we thought we had all the understanding we needed for the Hall ROM. We thought we understood the levers on the symmetry control, so we scaled up the radius. And what did we get? Kind of the same as before. So initially, we struggled. So this is a plot again, same plot I've been showing, yield versus ion temperature, yield versus hotspot pressure. The new set of experiments were marginally better than what we had the previous 3 years. In the metric of hotspot pressure, we actually lost. And so initially, this strategy struggled. And pressure on us became intense. One of the things that really surprised us was capsule quality. So we thought by making the capsules bigger, the capsules are man-made objects. Nothing man-made is perfect. There are always defects in anything man-made. But we thought we'll make the capsule bigger. Surely the defects aren't going to get worse, right? Defects are kind of set by some microscopic scale. So relative to the size of the capsule, the defects should be less important when we make the capsule larger, not more important. Mother Nature didn't agree. So we were surprised when we scaled the size of these capsules up that the problems with engineering defects in the capsules became much worse. And it was a shock, and it set us back a lot. What are some of the defects? Well, here's our diamond capsule. If you take a little cutaway and you look at the through thickness, all of a sudden you saw voids inside the through thickness. You saw high Z particles where they weren't supposed to be. You can see there are two different layers of material. There are supposed to be layers of material in there, so that one's supposed to be there. But why is this happening? We saw big holes in the through thickness. That's almost like the ablator's turning to Swiss cheese. You look at the surface of the capsule, it kind of looks like the surface of the moon. Why are all these pits there? And so this was a shock, because we thought we had engineering control of the capsules, and we realized we didn't. And there was a lot of work done by the target fabrication team to realize that, well, a lot of this is art as well as engineering, right? These are artisans making these things kind of at the edge of what they know as engineers. And that becomes like an artistry part of this. And we realize we don't have control of manufacturing these as well as we thought. Why is this an issue? Here's another movie. So here's our hot spot that we want to be hot, right? What you're going to see is a feature shooting in from the side and entering that hot spot. That feature that shot in is correlated with some of these defects in the ablator. And I'm just showing you a movie because it's a pretty good quality movie, and one feature. When you have all of these defects, you have multiple features. Okay, so why is something coming from the ablator bad for the hot spot? It kind of looks interesting. And let's talk about the physics of that. Okay, the physics of why shooting material into our hot spot is bad is something we term mixing. That's another jargony term. It has to do with the power balance inside this configuration of the hot fuel surrounded by cold fuel. So what we're trying to do is get a lot of alpha heating, as I described earlier. So the alpha heating goes as a function of the density, the fusion reaction rate, some number out front. And the alpha heating is battling against cooling processes in the plasma. And we talked about this in words before. We have Spitzer thermal conduction, that's electron conduction. That's trying to take heat away from the hot part of the plasma. The way we battle against this is to increase the rho R, and that's why compression is important. The other loss that we have to compete against is Bremsstrahlung loss. And Brems, if you're like in the physics program, that's breaking radiation. That's the tendency of charged particles when they accelerate to emit X-rays. If you're not in a physics program, it's just X-ray emission. It's just radiation. So imagine, you're standing by your oven. You can feel the heat coming from the oven or from a fire. That's radiation you're feeling, although that's IR, not X-rays. So now how does this relate to the capsule defects in the particles? The Bremsstrahlung X-ray loss increases as the average atomic number squared. So if you have deuterium, pure deuterium, that's an isotope of hydrogen, Z bar is 1. But if you have carbon, Z bar is 6. You just go up the periodic table, they're all numbered. The higher up you go on the periodic table, the more BREMs you're going to get, and it goes as the square of the BREMs. So as you inject material from the ablator, which are materials higher up on the periodic table, into the hot region of the plasma, there's a tendency to radiate more, and a lot more, like mad. That steals energy away. So this is a plot from some computer models I made of yield amplification versus energy. And I've been emphasizing the importance of energy in this talk. If you have a fusion system where you see ignition, the sudden increase in fusion yield at a certain energy where you didn't have any mix, but which are these high Z particles being thrown into your plasma, and now you introduce mix, you're pushing the energy you need to get ignition further to the right, and it costs you energy. And you might be able to afford that energy cost, or you might not. We've been working at the edge of what our laser system can deliver for like a decade. We really can't afford it. And so that's why this is such an important process to control. It's interesting that the energy scaling between the mixed and no mixed case goes to the Z bar 0.6. I find that interesting, maybe no one else does. All right, so what happened? Well, we finally got more energy. And this was a long-term effort by the laser engineers at NIF. We actually realized from the high foot implosions, we really would like more energy. We've been begging for more energy. And it took like half a decade of them trying things out, the technology improving, them figuring out some problems with the laser to try to deliver this capability. But, you know, last month we had the first case where we could actually experimentally test this with a target in the center of the chamber. So they were finally able to push the NIF from 1.9 megajoules of laser energy to 2.05. Here's our fusion yield versus temperature, fusion yield versus hotspot. That most recent result is shown up here on the upper right. And again, kind of this is our story of progress, starting down here, ending up here, starting down here, ending up here. So we now have pressures that are over twice the center of the sun, temperatures about 10 times the center of the sun, fusion yields in this case of 3.15 megajoules as compared to the 2 megajoules of laser energy, 2.05 that went in. So we've, by addressing, this is a story of like addressing problems in steps over a period of 10 years. And by doing so, and using kind of basic principles understanding with our computer models, with empirical physics, coupled with a lot of design optimization finesse, we were finally able to go from 1.5 kilojoules to 3.15 megajoules. Okay, so let's talk about the design that actually has resulted in all of the big breakthroughs the last couple of years. The design is called the hybrid E design. We've done a B, C, D, E. This is the hybrid E design. It actually looks a lot like those cartoons at the beginning of the talk. It's a gold hologram, a capsule. The details here are what are mattering, the dimensions of all of these, the details of the laser pulse. The key elements that went into making this work were a 20% larger radius capsule than we previously did back in that 2015 to 2018 period. We reduced the laser entrance holes to try to constrict them as much as we could to balance out our symmetry control while not letting X-ray energy escape. And that required that understanding I discussed and the crossbeam energy transfer. We extended, we used lower laser power but extended the duration of laser power to reduce the coast time, which we knew was important based on those old results and our physics understanding. And this all resulted in an increase in the hotspot energy and pressure. Here are the two most, these are neutron images of our two most publicized results. Our shot from a year and a half ago, 210808, which you can see is not perfectly symmetric. It yielded 1.37 megajoules. This is a neutron image, a 3D neutron image reconstruction of our most recent shot from last month. 3.15 megajoules of fusion yield, and you can see it's pretty round. You don't have to be an expert. What are the differences? It's basically an 8% thicker ablator, again leveraging that mass of the shell with 8% more laser energy. That's shown here. Here are the two laser pulses associated with those shots, and it's really this extended duration of laser energy at the same power coupled with that thicker ablator that led to that recent result. So by increasing laser energy and capsule thickness by 8%, with symmetry control, we attained a target gain greater than 1 on December 5, 2022. And this is a plot in what's called Lawson metric space. It's the hotspot pressure times confinement time times temperature. Here's where we were stuck for years. We started down here. We worked our way towards the ignition boundary and then passed through. And here's that most recent shot. So that's basically a story of success by incremental improvements that were evolutionary rather than revolutionary.
Dashed lines for the Lawson?
Yeah, so the Lawson, in this format, it's actually a three-dimensional space. So these lines, there are actually a whole family of them, and they correspond to different levels of mixing. So if you change the energy balance of your plasma, where you're radiating more, where you cross the ignition boundary changes, it moves to the right, because you have to fight against Bremsstrahlung losses. So these dashed curves represent sort of an uncertainty bound, knowing what our uncertainty and mixing of our different plasmas are. But it's basically a third axis out of the board, and most people can't rock the 3D plot, so we plot it in 2 dimensions. Okay, so we do still have outstanding problems. We haven't solved all problems. One of the outstanding problems we still have that has been frustrating and forced us into this different strategy is our materials don't seem to compress as much as models expected them to. So this is a plot of a database, at least up until 2021. This is a measure of compression of our materials versus that measure of entropy called the adiabat. We expect it to lie on this line, but you can see most of our data falls well below it. So we're getting a lot less compression for our adiabat than we thought. The reason why this is important, if we ever want to get the burn efficiency up and get a lot more fusion yield out, we're going to need to go and get higher compression out of these implosions, and we don't quite know how to do that yet. So this is the end of the beginning. There's more work to do. And so I'll just get back to that conclusion slide I had at the beginning. What's remarkable now is that we can now talk about burning plasmas, ignition, and scientific break-even in the past tense. And these are the same conclusions I had before, and I'll just stop with that. Yeah.
Thanks a lot. Bob. Yes.
Yeah, let me start off. I got a tad confused at the end when you added the capsule control, getting rid of impurities in the capsule on the one hand and increasing laser power on the other.
Yeah.
So this last stretch,
Yeah.
how much came from?
We don't know yet. It was a month ago, so we don't know. We're asking that question ourselves. They both go the right direction. Yeah.
Could you talk about the challenges to get from here to net energy gain?
Yeah, so the biggest challenges that we have are, one, we have to get the gain of our targets up. So these results are a gain of 1.5. That doesn't make up for all the energy lost in the laser. So you need to get up to gains of, people expect optimistically gains of 40, pessimistically gains of 100, so versus 1.5. We have to get a laser that's a lot more efficient, because this laser is based on technology from the 1990s. It's only about 0.5% efficient. So again, you get 300, 400 megajoules of energy in for a 2 megajoule laser beam coming out. I'm told by laser experts that using today's technology, you can make lasers that are 10 or 20% efficient. In addition to improved laser efficiency, you have to be able to shoot rapidly. So NIF is a research facility. We can do 1 to maybe 3 experiments a day. To do one of these cryogenic experiments where you get fusion yield, it usually takes a whole week to set it up. For an inertial fusion energy plant, which is what you're implying, you have to be able to shoot 10 times a second. So that's a big difference in rate. The final thing is the targets. Our targets that we have for these experiments are complicated, they're expensive, and they're fragile. And we gingerly carry them to the target chamber, mount them on an arm that puts them in the middle of the target chamber. A lot of times they break before they ever get to the experiment. For an inertial fusion energy plant, that would never make sense. So we need a much more robust target that still satisfies all the physics needs. and that won't just kind of fall apart before being shot. So there are a number of engineering challenges that would have to be met to take this kind of scientific result to a practical energy result.
So now that you're starting to understand what's going on, it's kind of amazing after 25 years. The world has gotten to this point.
Yeah, we're slow. I went to public schools. Yeah.
One simple way of getting more oomph out of the laser is to back off from 3 omega to 2 omega. There are good reasons to stay at 3 omega, but have you looked at
People have looked at that. They're advocates for 2 omega, what we call green light. The two issues. Green light tends to couple less, so you get more energy out of green light delivery than blue light, but it actually couples less in terms of fraction to the target. The other thing is the bad experiences Livermore has had in the early years of the inertial fusion program, starting back in the 70s, where we got a lot of laser plasma instability from red light, which is what they started with. They skipped over green light and went straight to blue, but there's fear of green lights. Nevertheless, people are looking at it. We're thinking about it because ICF is all about trade-offs. You do something that you think helps you more energy, and then you hurt yourself somewhere else. So it's a kind of high parameters, large parameter space optimization, and yeah. So.
One question back there.
What percentage of this new design of capsule actually underwent ignition?
So most of the fuel in these experiments is wasted. The burn-up, the term that we use for that is a burn-up fraction. So the amount of fuel that was burned up on these most recent experiments was 4%. The experiment from a year and a half ago was 2%. That equation I showed on the second to last slide, which was rho r over rho r plus 7, tells you what your burn-up fraction is. If you can get compression up, get that rho r up, we could, in principle, go up to burn-up fractions of 10, 20, 30%. And that's why compression is so important. You will never get 100% burn-up. You won't even ever get 50%, and I'm skeptical we'll ever get 30% because compression is so hard. That's actually a lot better than magnetic fusion, by the way.
So I guess I was trying to ask something slightly different. That's within one capsule, you're saying. We don't use all the fuel inside of one capsule.
Yeah.
Okay, sure. I was saying you would have multiple runs of this new type of capsule, right? Like how many of those, you have a standard for saying that we've reached ignition. How many of these same design capsules actually reached your standard?
Oh, okay. So yeah, that was basically on this plot here. Basically, we have 3 shots that have ignited, which are these. These are kind of on the boundary of ignition. They're where those dashed lines are. So far we've gotten 3 ignition by the thermodynamic instability / loss in definition. We have 1 which satisfies this target gain greater than 1 definition. Okay.
If we could look at, the 5th point there about high gain target designs not working so well. Could you briefly kind of elucidate what's different about the target designs for what you call a high gain target and a low gain target?
So the key difference is a low gain target would have a high picket, which means this early part of the radiation temperature in the Hall realm is higher, which means there are much stronger shocks launched into the implosion. Those much stronger shocks result in stiffening the DT fuel, making it harder to compress. So a low gain target would be one where we can't compress as much. A high gain one would have this be very low. The early time radiation temperature would be low. We launch gentle shocks into the implosion. We make it more compressible so we can squeeze it up more. And the result of that would be a higher aerial density. And that allows the implosion to blow apart less rapidly than a low gain target would.
So just to clarify, the the distinction you're making, the actual geometry of the target or the actual geometry of the whole
doesn't change.
Similar for the two cases?
Yeah, it doesn't change at all.
Different?
No, it doesn't change at all. For example, the low foot implosion in principle was a high gain target, high compression target, low adiabat, low foot. We used exactly the same physical target for the high foot implosions, which were low gain, high adiabat, low compression. The physical target does not necessarily change. It's all controlled through the laser pulse, which controls the entropy, which controls the adiabat and the squishiness of the implosion. They can be different, but they don't have to be.
Thank you.
What would happen if you could increase the laser energy power tenfold?
Yeah, it makes jobs easier.
Because everything I heard scales bigger and bigger.
Yeah, bigger. One of the most people don't realize a big implosion is actually easier than
Hydrogen bombs told us that.
Yeah, okay, so some people know that. I mean, that's why we have hydrogen bombs in the 1950s, and we only got this working last month. Small implosions are much harder. And it's basically, the key quantity is energy. Oh, that doesn't write very well. Energy times pressure squared has to be larger than some number. So if you are limited in energy, you are forced to generate higher stagnation pressures at the center of the implosion. But if you can deliver more energy, you relax.
What's the trade-off of getting 10 times more energy? As a laser person, I would say, hey, that seems easier to do than playing all this really finesse stuff.
It's just money as far as I know, right? It's there's plenty of that, right? Time was money. But, we were kind of stuck with the facility we had. So, and it took a long time just to squeeze a little more energy out of it once the design was fixed because of the scale of the facility. And it required technology improvements too. The other thing is, I think higher laser energy is really damaging for the optics. So there's a carrying cost associated with the high energy laser that you know more about this than I do. So
But there, the dielectric breakdown, and so you just make everything higher diameter until right?
yeah, it's and again, then the scale of the facility becomes larger, so there's a cost. So it's just money. It's I would take it. Yeah, that would have.
All right, let's see. Roger?
Okay. I have a sort of elementary confusion here. That given your cylindrical symmetry, it would seem like you're virtually guaranteed to be jetting a lot of energy out the axes. And it seems like you only can compete with this with the two different pitches of the lasers coming in. Presumably there are other things that you are doing to symmetrize the implosion. Otherwise, it seems completely hopeless.
It's not completely hopeless. Because we've been successful. You can, again, it's an existence proof that it's not hopeless. It is difficult. One of the things we've also looked at is changing this geometry. I've only showed you right circular cylinder cans, but there are a whole bunch of concepts, many of which we've implemented and tried, where you actually change the geometry of this can. A lot of people like ones that are more sympathetic with the spherical shape of the capsule. A football shape, we call that a rugby. So we've done experiments with those where you try to change the geometry of the can. We've also tried to change it the other way. Instead of a rugby shape, which you'd say that's more sympathetic with a capsule, you try the opposite. There are a whole slew of concepts. The sky's the limit in terms of.
You're still using cylinders, so they're not helping much.
Yeah, exactly. They're not. And there's a practical aspect that maybe is communicated. And to learn how any one of these works takes a lot of experiments. So say you want to switch to completely different geometry. You have to make a choice. Do you want to give up on your database of understanding where you have experimental data with one particular geometry and start over on the hope that the new geometry might be more beneficial? And it may or may not, and then you have to basically acquire a whole new set of data to understand how it works. There's probably going to be something there that you didn't think of that's going to frustrate you, and yet another challenge. So there is a you have to make this choice as an applied scientist. Do I keep pushing the tactic that I know, or give up on it and try something completely different? And I don't think there's any clear answer on that always, unless you basically know this is hopeless and then it's not going to work.
So I actually have a related but more extreme question. How about direct drive? Is that entirely out of the question?
No,
from
no.
what you've learned? Or
No.
that would be simpler, in terms
direct drive has a couple of advantages. Direct drive gets rid of the Hall-around, and there's as I begin to talk, there's about a factor of 10 energy loss in using the Hall-around, and that conversion of laser energy to X-rays with that much smaller capsule inside. It basically goes as the surface area of the Hall-around compared to the capsule. That's the fraction of energy loss. You get rid of that step, so you can deliver a lot more energy to your target, which is kind of the point you had. The downside of direct drive is ablation-Rayleigh Taylor instability, because X-rays, because of the wavelength of light, they tend to make a less steep ablation front on the outside of the capsule. It's more gentle. Because direct drive deposits its energy into the implosion through electron conduction, the electron conduction mean free path is much shorter than the wavelength of light. So you get a much steeper ablation front. So hydrodynamic instability-wise, you are at more risk for losing control of the instabilities with direct drive than you are with indirect drive. And there's a trade-off there, because you can perhaps engineer your way out of that. But it's again, there's no free lunch. You always trade something for some benefit for. And people, I mean, there's our sister lab, which is one of our partners, Omega, which is the Omega laser at the Laboratory for Laser Energetics. All they do, 95% of what they do is direct drive experiments. So it's not like that's being ignored.
All right, let's see, one more question. Yes.
You talked about the energy that's released in the implosion. What about capturing energy from the neutrons in the opposite?
Yeah, so the reason people have thought about that, and I'll tell you the schemes that people propose for that. Again, NIF is not a fusion energy research facility. We're a research facility mostly with interest in national security matters. The way people have thought about capturing the energy from fusion for practical use is to use a lithium salt blanket around the facility. So kind of take that target chamber and imagine another layer where you're flowing lithium salt inside that interstitial region. The neutrons from the fusion plasma hit that lithium salt and they deposit energy in it. That makes the salt hot and makes it molten salt. And then you flow it around to a heat exchanger. On the other side of the heat exchanger is water. You boil the water, you make steam, you run an electric generator. The other thing that lithium salt does is when the neutron hits lithium, in particular lithium-6, which is a minority isotope of lithium, you can, what we call crack it, you break it into pieces, and you can make tritium that way. And tritium is a necessary part of a DT fusion reaction that is not available in nature because it has a 12-year half-life. Deuterium, which is the other component of DT, is available in seawater, and lithium is available in seawater in kind of copious amounts. So lithium blankets are the primary concept that people in fusion energy think about in terms of extracting energy out for practical use. So.
All right. So we should thank Omar again.
Yeah.
Yeah, pretty good.